All right, so let's continue our second half. So if you look at this matrix B, first of all, then you have to, tell that what size of the matrix. In other words, when you see matrix, then is that 2 by 4, 10 by 3, or whatever the size of matrix, you should be able to identify immediately, as long as you know what kind of problem you are solving, and then what type of element are you using to solve the problem. Once you decide that, then you should be able to determine what size of matrix B, as well as, of course, the column vector D. All right, so this depends on, first of all, the dimension of the problem. Is the 1D problem, 2D problem, 3D problem in serial velocity state. Why? Because 1D problem, you have only one displacement. For example, U. If you have a 2D problem, you have two displacement, U and V. And 3D problem, you have a U, V, W, three displacement. Okay, so that depends on the nature of the problem. And then the other one is going to be what kind of final element to use. For example, I use triangle element, 3-node triangle element. Then it doesn't matter whether this is going to be conventional or isoparametric element, doesn't matter. 3-noded element. That means each node, let's say go back to this problem, 2D problem. Each node has how many displacement? 2, U and V, and 3 node. That means total, each element has 6 degrees of freedom. UV, 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 node 1 to 3. So 6 degrees of freedom. So that means column vector D is 6 by 1. Okay. And what about matrix B? Matrix B, the number of row, again, depends on either 1D, 2D, 3D. 1D, you have only one string. So 1. Okay, number of row is going to be 1. 2D, you have a 3 string. So 3, always 3, And this is going to be 3D. Then you have a 3 string and a normal string, 3 short string. So that's 6. So number of row is going to be either 1, 3, 6, depending on 1D, 2D, or 3D problem. And number of column depends on your degree of freedom of the selection of elements. So if you use that one, then how many degree of freedom? 6. So that is going to be 3 by 6. Do you get it? If I use 1D problem, like that one, then this matrix P is going to be what? 1D problem. 1 by how many degree of freedom? 1D problem. 2 nodes. Each node has single degree of freedom. So this is 1 and 2, like a U1 and U2. So that's going to be 1 by 2. All right. And what about this? Four-noded 2D element. What's the size of matrix B? 3 by? How many degree of freedom? Each node 2, but element-wise. How many? 8. So that's going to be 3 by 8. You follow me? I'm going to ask one more time. What about tetrahedral in 3D? This is the simplest 3D element. What size of this matrix B? 6 by 12. Each node has 3 degrees of freedom, 4 nodes, so 12. So B is going to be 6 by 12. Right? Now, another common element. This A node box shape element. What's the size of matrix B?
Are you asking for 3D?
It's 3D. Box is 3D.
6 by 24.
6 by 24. Why 24? 8 node, each node has 3 degree of freedom, so 6 by 24. Right? So, in other words, you should be able to recognize that. Then, once you recognize that, the order of, the shape of this matrix B, that if the format is exactly same kind of format, regardless what kind of element you use. In other words, this is for this element. This matrix for this element. If I use this matrix, you are going to add what? 2 more column vector. So if you look at that, this one for H1, and this is for H2, this is for H3, right? Exactly same format. 1, 2, 3, that's different, but X, 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 Y, 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 X, Y, X, Y, X, exactly same, right? So if I have to do for that one, then that's going to be same 2 column, repeat here, but this subscript is going to replace by H sub 4. So partial H4 over X, 0, 0, partial H4 over Y, and partial H4 over dy, and partial H4 over dx. So exactly same expression is going to repeat over and over. Make sense? So the shape itself is going to be very consistent, depending on element and depending on also the dimension of the problem. Right? All right, then the last thing we are going to show you in here is that in this expression, so this is replaced by B and D. This is replaced by B and D, as shown in here. Okay. Then what about this one? That's the test function. Test function 1, test function 2. Okay. Now, if I use Galerkin's technique, then what is the feature of Galerkin's technique? Galerkin's technique, we use same sheaf function or the test function, right? The test function is equal to sheaf function. And in this triangle element, linear triangle element, I have 3 shape functions, H1, H2, and H3. So this W1, W2 are going to be replaced by H1, H2, and H3. In other words, what I'm saying is, I hope you understand that exactly what I'm talking about. So W1 is equal to H1. Okay. And W2 is also equal to H1. All right. So I pick H1 for W1 and W2 respectively. And next one, now I pick H2. Both W1 and W2. And finally, I use H3 for W1 and W2. Okay, so that's the Galerkin's technique. I use same shape function for test function. So W1 change 1 to 3, W2 change 1 to 3. So that's the when H1 is used for W1 and W2, and H2 used for W1 and W2, and H3 used for W and W3. So that's going to be 6 by 3 matrix out of this one. So this is going to be expanded to this one. So this concept come from the Galerkin's technique. And if you have any problem going from here to here, that means we have to review chapter 2 one more time. Okay, for Galerkin's technique, we pick shape function for the dryer, the test function. And then you got 3 different test function for W1 and W2. So we pick this one. So this is going to be, happen to be 6 by 3 matrix. Any question for this one? Okay, then I believe you understood that. And again, if you have any problem, you need to let me know. But once you are comfortable with that one, then look at this. What is this expression, this matrix? Have you seen me? That's going to be? Oh, what is it? This expression. And what's the difference? Change it, that means mathematically, what do you call? Transpose. Transpose, right? So this is equal to matrix B transpose, right? So column become row, row become column, transpose. So what does it mean? This term, oops, there are too many papers here, so please bear with me. So going back to here, this term is going to be equal to B transpose. So what this term means is shown in here. B transpose D times B, that's the expression. Okay. So here is very important aspect and simple aspect. Your element stiffness matrix in solid mechanics, okay? Zero velocity and structural mechanics eventually same thing, but element stiffness matrix is going to be expressed always in this expression. B transpose D times B. Whether this is 1D, 2D, 3D, or what kind of finite element you select, doesn't matter. The format is going to be always B transpose times D times B. Yes.
What's the difference between this stiffness matrix that we derived versus the ones that we derived in earlier chapters?
All the chapter 8. So like a beam element and that also can be put in this manner too. We haven't done it. But if you want to put that on also in this format, exactly we can put in this format too. So this is going to be very broad expression, okay, applicable for many solid mechanics problems, including zero velocity. So then you have to clearly understand this symbol, B transpose times D times V. So what is B, what is D, right? Then B is the matrix relating strain and displacement. like this one, derivative of the, shape function. So relating strain and displacement, that's the matrix B. So we talk about size of matrix B. So size of matrix B is going to be either 1 by, 3 by, or 6 by, and something like this one, 3 by 6, 3 by 8, 6 by 12, 6 by 24. Okay, so that's going to be size of matrix. Then what is the matrix D? Matrix D is the constitutive equation. In other words, the relationship between stress and strain. Okay, so which is shown in here, like a plane stress and plane strain, shown in here, to matrix D. So size of matrix D is clear. Either 1 by 1, if this is going to be 1D problem, and 3 by 3, this is going to be 2D problem, and 6 by 6, if this is 3D problem. 1 by 1, 3 by 3, 6 by 6. A square matrix. And this one does not depend on the choice of element, just depends on the nature of the dimensional problem. And actually the property depends on the material behavior. Isotropic or orthotropic, anisotropic, whatever, depends on that. It changed, but not because of selection of different type of finite element. So 1 by 1, 3 by 3, 6 by 6. Okay, so if you look at the nature of this one, then this is going to be, for example, this one. B is going to be 3 by 6, right? 3 by 6 right now. And this transpose, 3 by 6 transpose is going to be 6 by 3, correct? Change the column and row. And matrix D is going to be 2D, 3 by 3. So this is going to be total 6 by 6. And this is going to be 6 by 1. So everything makes sense. All right. So if you imagine what the commercial code does for your, solid mechanics calculation. In other words, I'm going to do this stress analysis using this type of element. And this is, if you provide a mesh, then they know this is going to be 1D, 2D, 3D immediately. And then you select, I'm going to use this type of element. And then I'm going to say this, the linear elastic isoparametric isotropic material. Once you provide that information, then program, okay, pick the matrix D, depends on your material and dimension. So there's library, they pick that. And depending also dimension and, shape function you select, then they calculate matrix B. And then they are going to calculate this one over and over for every element. That's the way they can write so-called general purpose program. The program can do many different things within the single, framework. They don't have to write one program for one calculation, another program for another calculation. No, it's not like that. You can do that because you have very generalized, formulation. B transpose times D times B. Some textbook, they use this one for E, matrix E, just matter of notation, either B or D or B, E, T or E, but mostly consistently they use matrix B in here. Of course, just matter of the notation. You can use, I want to use matrix A or C or, whatever they want to, perfectly fine, as long as what that means. This is matrix, we are talking about matrix B, okay? But typically, many textbooks use B, so B transpose times either D or E times B. Okay, so that's the expression. Any question up to this point? All right, then let's evaluate this matrix B because matrix B is important. Matrix D, we already have that in the previous, note that for at least trophy material. So this is going to be constant matrix. And if it become elastoplastic, in other words, if the material property like this one, if this straight, then this is going to be constant, okay? But if you're talking about stress strain curve goes like this, so it becomes like that one. Then now material property is not constant, so this is going to change as we apply the laws of the proper strain level. You're gonna have a different property, so this is going to be changed for elastic, plastic, or non-linear, material behavior. But the linear material behavior, that's going to be always constant matrix. Okay, so you don't have to worry about any changes. But matrix P, let's evaluate this one for this triangular element. Since we have the shape function, at least for conventional one to begin with, then if you calculate matrix P, P is going to be written in this manner. All right, we have already expressed this one in chapter 5, so this is a repetition of that one. And again, A is area, as long as we pick this one, it's going to be counterclockwise direction. 1, 2, 3, 4. 1, 2, 3. Okay. I said that this is area, if that one, but otherwise it's going to be the negative of the area, because that could be plus and minus mathematically, but area is going to be always positive, physical manner. So that when you say, pick 1, 2, 3, as we did in chapter 5, A is going to be area, so you got like that. Then what does it mean? This has very interesting property, which is important, is that B is strain is B times T, and stress is T times strain, or T, E, and T. So those are the nodal displacement. Node 1 to 3 of displacement UVW. So that's going to be just constant column vector, whatever displacement, constant column vector. But if you look at that, matrix P, if you look at that one, what do you see? Matrix P is it a function of X and Y within an element? Is it a function of X and Y? Yes or no? So this is X1 and Y1, and this is X2 and Y2, and this is X3 and Y3. Those are the nodal coordinate, 1, 2, 3. So if you look at matrix P, any component out of this 3 by 6 is function of X or Y or not. In other words, what I'm saying is that within element, okay, again, 1, 2, 3. If I look at this point, if I look at that point, if I look at that point, the strain matrix P is going to be different or same? Same, right? There's no multiplication multiplied by X or Y in this term. Everything is going to be based on the nodal coordinate 1 to 3. That means any point your matrix P is going to be constant. Correct? In this formulation. So that means this is constant. That means this is also constant, because matrix T is going to be constant, at least the linear elastic. So constant. What does it mean? If I use this element, strain and stress, we are assuming they are constant within the element.
You move the paper a little bit.
Oh.
I've been seeing you.
Sorry about that.
Thank you.
So this means within element, the stress strain does not vary from point to point, just one value for the whole element. So what does it mean? If I go back to the mesh, Here's my mesh. If I don't, then I can redraw that. Yeah. I have a mesh on there. Yeah. That's okay. And I can redraw the mesh. So if I have a domain and mesh like this, okay. Like that, let's say. Then displacement at nodal point are going to in general different at every point depending on the deformation. But if you are going to calculate strain and stress, then in this element, for example, in this element, epsilon x, epsilon y, gamma sub xy, of course they are different, they are not same, but this is going to be constant within element. In other words, if I take this point, that point, doesn't matter, everything will be constant within inside element. Same thing, stress. However, the stress or strain in this element and stress strain in this element are going to be different. Here, it also has unique strain component or stress component. Okay, so stress value and strain value, one set of value for this element, one set of value at that element. Same thing, next one, you have a different stress strain, but constant within element, etc., for the rest of them. So what I'm saying in here that, then if you look at this element, that element, they are neighbor together, right? But the stress here, let's say, to make it simple, I have element looks like this. So this is going to be y direction. Okay, then sigma x here and sigma x here. This element, that element have two different values, in my final element calculation. Here, let's say 1000 psi. Here, I have 1200 psi. So different. Then it is not correct because that at this surface, at this interface, you have to maintain equilibrium. That means stress on the left side, stress on the right side have to be equal to each other, right? That's the right solution. Okay. However, this final element of so-called linear triangle element, and this called also constant stress and constant strain element, constant stress or constant strain element. Okay, this linear triangle element does not satisfy those equilibrium at the interface between two neighboring elements, unfortunately. Okay, so as I said, this is going to be 1000 psi, that's going to be 1200 psi, that's it. So you do not satisfy exact equilibrium at the interface from element to element. So that is an approximation. So in other words, your final solution is not going to be exact, but still good approximation of the nature. Then how do I improve that? How do I improve that, the accuracy? Obviously, you have to, what? More node or more element. So make element size smaller and smaller. Then the difference becomes smaller and smaller. Eventually, you are going to satisfy that element interface, stress condition. So that is the approximation. You have to accept that. Okay. So final element approximation does not satisfy everything exactly because that's the approximate solution. So at least at the interface, they do not satisfy that stress equilibrium. Make sense? But deformation is going to be continuous because we cannot have some, jump of the deformation all of a sudden, which is not physically acceptable. So deformation is continuous, but stress strain may be incontinuous, some kind of jump from element to element because of that approximation. Make sense? And because of this nature, and again, because this is going to be constant, it's not a function of x and y. So if you evaluate this matrix, that's we talked about in chapter 5 also. If you evaluate this matrix, which is going to be exactly the same as this one. B transpose times D times B multiplied by area. So you don't have to really carry out any integration of x and y because of this going to be constant matrix. So that's why this element has been developed the first time as a continuum element in 1960. All right, you don't have to worry about integration anymore. Make sense? But it's not that accurate, right? Even you may have noticed in your first project, when you use triangular element, then the solution is usually less accurate than rectangular element. Okay, so to improve the solution, you have to refine the mesh. But anyhow, so that's going to be K matrix. And then if you're going to use isoparametric formulation, you can still do the same thing. In other words, you know how to calculate this matrix D, matrix B here, right? Using the isoparametric element. One of the example you did that in your midterm exam. So dH1 over dx, dH1 over dy. You can evaluate this one for the isoparametric element. Then eventually you have to carry out this one, okay, using numerical integration, like a Gauss quadrature, or depending on what kind of element you are using, you have to do numerical integration to come up with this one. That's what, again, the most commercial program does, okay? You use isoparametric element and then carry out this one numerically to calculate your element stiffness matrix. Right? This is a very special case. Okay. Any question up to this point? All right. Then we took care of this this term. The first term. What is the first term? In here. Okay. So let's look at this term and that term. Right? So the body force term, if you have a body force, again, this is the domain integral. So you have to do for every element in your the mesh. And W1, W2, this expression is going to be written this manner, which is same as that, right? W1 times Fx and W times Fy. And then now this is replaced by, again, the shape function in Galerkin's technique. So this is going to be one. When I use linear triangular element like that, H1, 0, 0, H1, when I use H1 for both, and H2, 0, 0, H2, right? And then H3, 0, 0, H3, right? For this element. If you have this element, then you are going to have, again, two more rows in here. But this is good enough. This is it. Then what is this one? Again, I have seen this one. Okay, it's not new, which is going to be in here, this transpose. This is equal to that with transpose, so that this is going to be N transpose time this body force, XY component.
Professor,
Any question? Yes.
why do we label the test functions 1 and 2 when we're just going to use the same shape function in each?
So this is the test function, right? Test function for the first equation, second equation, right? This is W, even I
Mhm.
used the omega, but it's actually more W. So in Galerkin's technique, if you remember what we talked about in chapter 2, Galerkin's technique, then test function, we use the try function for test function, right? Except the coefficient. So try function is H1, U1 plus, for example, H2, U2 plus H3, U3. Oops. Plus H3, U3. So W1, because I need same number of equation as unknown, that's why you need W1, W2, W3, I mean, the multiple expression. So that is going to be, W is going to be DU, D, either U1, U2, and U3. Okay, this is like A, B, C in the continuous, the formulation. So that is equal to H1, H2, and H3. So those are going to be the test function for W. In chapter 2, we start with that one. U is going to be A, for example, X, 1 minus X. Then W is going to be DU, D8 is constant to be determined, so X, 1 minus X. That's what it did in chapter 2, right? So this A, this is the generalized coefficient. This A is equivalent to here, nodal displacement U1, U2, U3. So in other words, in this case, you have one variable, so take just one derivative and then one test function. But here, you got U1, U2, U3, three different variable. So I need to take a derivative with respect to U1, U2, U3. That's what you get, H1, H2, H3. So you got this three shape function, exactly same as what you use for your solution U. Do I answer your question or?
Yeah, I think I understand that. I'm still confused on why we use the W1 and W2.
W1, W2 is that going back to here, the first equation is multiplied by W1 and second equation multiplied by W2. All right, this one test function, this is going to be another test function.
Gotcha. And so we just,
Got it?
yeah, but when we evaluate it, we use the
Yeah.
three shape
So if you have a
functions.
third equation, then that's we call W3 because it doesn't have to be the same. W1, W3, or W4 depends on how many equation. Okay. Then now this is the test function for the first equation, test function for the second equation, test function for the third equation, test function for the fourth equation, like that. Huh? Then each test function is going to vary based on the shape function.
Gotcha. Okay, so
Like,
just to denote which equation.
yes, U and V, I use the same shape function, right? So likewise in here, W1 and W2, I use same shape function, H1, H2, H3, same shape function.
Got it.
Thank you. Thanks for asking. So that's the body force. Now, the more important, part is going to be the traction, surface traction. So this exactly looks like the heat flux in chapter 5. Okay, the flux and traction on the surface of the body. But now the difference between flux and traction, flux is scalar quantity and traction is going to be a vector quantity. So you have to differentiate between, among traction, X, Y, and Z direction, you cannot add them together. Okay, flux, it didn't matter. You can add flux in the x direction, y direction, and z direction at the same point, add them together, scalar manner, not a problem. But now traction, you have to calculate for x, y, or z, if it's going to be 3D, then you have to deal with that individually, not combining them together. So that's one major difference. But the procedure is going to be very similar to what we did in chapter 5. So we'll continue that on Thursday. Okay. All right. Any question up to this point? Okay, then I'll see you on Thursday. I'm going to stop recording here.